I will begin with a word of prayer. Heavenly Father, we again, Lord, thank you for your many blessings. And we thank you that you're a good God and that you love us even when we don't love you. Just pray that you glorify this time. Just help us to glorify you, And just give us understanding today, Lord. In your name I pray. Amen. All right. So I have example 1, example 2, example 3. So I'll do these for you. So we're trying to parameterize these 3 curves. So basically, what I want to do is complete the square on this one. That gives me, let's see here, I just added 4 to the left-hand side. So to be fair, I need to subtract 4 from the right-hand side.
Wait. You want me to just add 4 to that side as well?
Oh, yeah, wait a minute.
Since we're adding different sides?
Yeah, you're right. That feels better. I was about to say, well, anyway, yes, thank you. That makes more sense. I was about to say there's no solutions to this. And, well, that seems wrong. Definitely has solutions. Okay, so anyway, that's 5. And so I'll repackage that. That's x plus 2 quantity squared over 5 plus y squared divided by 5/4 equals to 1. The reason I do that is just to sort of give myself an idea where I'm going. I go, aha, but I know cosine squared theta plus sine squared theta is equal to 1, right? That's my thought. And so that suggests to me that I should put x plus 2 over the square root of 5 equal to, say, cosine of theta. And maybe I should put y divided by the square root of 5/4 equal to the sine of theta. And so in total, thus, I have x is equal to minus 2 plus the square root of 5 cosine theta. And I got y is equal to the square root of 5 divided by 4 sine theta. Now, of course, you could clean that up. You could write that as 1/2 square root of 5 sine theta if you wanted to. Right? Now, if you're going to be picky, if I just want to cover, the question then is how many times do I want to cover the curve? What is this curve? If I can draw a picture of it, it's centered at minus 2, 0, right? And it goes plus or minus root 5, left and right. It goes up and down, plus or minus root 5 over 2. Just about 1-ish. So this is an ellipse, right? So if I just want to cover the ellipse once, I would just say 0 less than or equal to theta less than or equal to 2 pi. If I wanted to cover the ellipse 2 times, I would make that range from 0 to 4 pi. If for some reason I wanted to cover the ellipse 20 times, I would make it 0 to 40 pi, right? Parametrically, you got that kind of freedom. So here I'm using theta as the parameter. If you'd like, we could erase the thetas and put t's. It wouldn't change a thing, except that I'm using t as the parameter then, all right? So that's one. Any questions? Yes, Josh?
How would you find the trajectory?
The trajectory.
The orientation.
you think about the formulas. So here, this would be t equals to 0, right? Where's t equals pi over 2? We plug in pi over 2. This is 0. This is 1. So pi over 2 is up here. Right? So if you look at that, it becomes fairly evident that it's like this. This is the orientation, right? So this is giving a counterclockwise orientation, which is usually taken to be the quote-unquote positive orientation for a curve in the plane. Yes, sir? If what?
If, like, let's say t equals 0, right?
Yeah.
And it's like t equals negative pi over 2.
Uh-huh.
Clockwise, right?
No, this parameterization goes counterclockwise. It's
If it was a different problem.
if it was a different, I mean, we could make a clockwise parameterization if you wanted to. If you wanted to clockwise parameterize the ellipse, you replace t with minus t.
Yeah, so it was negative pi over 2.
It would well, if you go the other way, if I write x, let's say x, if I was to write x equals to minus 2 plus the square root of 5, cosine of minus t is still, well, I'll just write it like that. Of course, I don't need to because cosine's even, right? If I take these and I set t equals to pi over 2, that will take me to the lower, this t equals 0 is still here, right? Now this is t equals pi over 2 for that new parameterization I just wrote there. So it's going clockwise. But that's a different parameterization. Okay. All right, I'm going to go on. I'm not trying to, I just want to give you guys a couple of crisp examples on how to find parameterizations of standard examples. So line segment, so what I do is, here I'll do it even easier. This is x equals to 1, y equals to 3, plus t times something, plus t times something, right? And so to get the right thing, I just take 6 minus 3, and I take, oh, I'm sorry, I did it the wrong one, minus 5, wrong component, minus 5 minus 1, and here 6 minus 3, and that gives me x minus 6t and y plus, oh, I'm sorry, I can't read my own writing, 3 plus 3t, right? For 0 less than or equal to t less than or equal to 1, that, I think that'll parameterize the line segment that goes from 1, 3 to minus 5, 6. Let's check my answer, right? If we put in, if we put t equals to 0, do we get that point? I mean, t equals to 0 gives me x equals to 1, y equals to 3, right? T equals to 1 gives me 1 minus 6, which is minus 5, and 3 plus 3, which is 6. So indeed, I do get the t equals to 1 here. Right. So let me see here. I could put it in a box. What I did was I said x is equal to x naught plus t times x1 minus x naught. And y is equal to y naught plus t times y1 minus y naught. Right? This, for 0 less than or equal to t less than or equal to 1, this will parameterize the line segment which goes from x naught to y naught, x naught, y naught, over to the point x1, y1. So this is a different way to remember that. I gave you guys a formula yesterday in terms of P and Q. Here's another way to look at that same formula, just in terms of a given pair of points. No vectors, right? I mean, I didn't use vectors. I personally think the way I did it yesterday is better, but whatever. This might be better for you. Here again, we need to complete the square. So we've got x minus 3 squared minus y squared equals to what? Plus 9, right? Which is 11. So we can look at this as x minus 3 quantity squared over 11 minus y squared over 11 equals to 1. But you guys know about Cosh and Cinch, and you know that the, important thing to know about Cosh and Cinch is that Cosh squared t minus Cinch squared t is 1, right? And let me just add some fine print to the original problem. For x less than 3. Okay, so this would suggest what then? I might try x minus 3 over the square root of 11 equal to cosh t, right? And I might try y over the square root of 11 equal to sinh t. But if you look at that, that's not going to work. The reason it's not going to work is I'm trying to parameterize the part of the curve which is less than 3. What does this thing look like? It's a hyperbola, right? It's centered at 3. Excuse me. Goodness gracious. 3, 0. Yowzers. It's got asymptotes which both have slope 1 if you look at it. And I believe it opens, let's see here, if I put x equals to 3, I get no solutions. Right? Put x equals to 3, we get minus y squared equals to 11. Minus y squared equals to 11, no real solutions, which means the graph does not cross x equals to 3. So this is one of those ones that open sideways. The graph looks something like this. Badly. It, of course, approaches the asymptotes. We're trying to parameterize the left half of it. All right? This puts us over here. Right? So I can't use cosh t for this half because that forces x to be bigger than 3. In fact, bigger than 4 times root 11. Let's see here. Let me make this 3 times root 11. That's more exciting there, just to be safe. Okay, so I suggest we just put a minus here, and that should take care of it. See, because then we'll have x equals to 3 minus 11 times the square root, minus the square root of 11 times cosh t for my x, and y will take square root of 11 times the hyperbolic sine of t. Yes, sir? Well, this, let's see here. So cosh, the thing about cosh, right, is that cosh of t is greater than or equal to 1. All right? Like cosh t looks like this, essentially, right? That's cosh of 0 is 1. So if I'm taking 3 minus the square root of 11 times something that's larger than 1, this could also be, I'm sorry, let me stop with this and just say what? What do I want? Left half of graph. If I was more with it, I could give you a honest inequality. But the point is, this, as t gets larger and larger, this becomes arbitrarily negative. Because you're taking 3 minus the square root of 11 times something that gets bigger and bigger and bigger as time goes on. If I put a plus here instead, I would have 3 plus square root of 11 cosh t. That will become arbitrarily large and positive, which is, I mean, basically has to do with, if I put a plus there, I'm parameterizing the other half, is what it is. So there it is. Anyway, these are the parametric equations for the hyperbola that I've given there. These are our 3 standard examples. All right. Now, you might also, I guess the example 4, which is just kind of a dumb example, is given y equals f of x, right? You can set x equals to t and y equals to f of t. This parameterizes a graph of a function. And the other thing that you sometimes run across, example 5, is just weird stuff like, I don't know, you could have something like x cubed y plus x squared y minus 3 equals to 2xy. Let's see here. Let me make it more exciting. Yeah, it's exciting enough. You get something like this and say parameterize this curve. So for this one, what I would probably do would be to see, this does not serve my this does not illustrate my still not a good example. It's too simple. Sorry. Something like x squared plus y squared times xy equals to 1 here. This is awful. Look at this. This describes some curve. I have no idea what this thing looks like, but it's something, okay? Parameterize this. How would you do that? Multiply xy the whole thing? I mean, okay. I'm not sure that helps, but I'll do it. All right, great. Divide by y. All right, I'll do it. I don't know if it helps, but I'm open to suggestions.
Could you set x times y equals cosine and sine?
X times y. All right, so these were not helpful. Let me just remove them from the record.
That makes x
What did you say again? You said set
x equal to cosine and y equal to sine.
x equal to cosine of t,
And y equal to sine of t.
y equal to the sine of t. That seems, at first seems promising.
Because that makes 1 over x squared plus y squared equal 1.
That's true. That makes x squared plus y squared equals to 1, which is great. That's nice. You've taken care of this piece. But the thing is, then you've still got xy, which is equal to cosine t sine t. Right? So when you plug these into there, you don't get 1 again. Right? If you try these formulas as a parameterization for this, it doesn't quite work because, I mean, you've solved one problem, but you've got another. There's two problems. Nice try. I like it. Nice try. What if we just say, I don't know, let's try xy equals to t. Right? If I do that, then that implies that x is equal to t over y, and y is equal to what? T over x, I suppose. I'm not sure this is really helpful either. I'm just trying something, you know? And great. So then this gives me t over y squared plus t over x quantity squared, right, times t equals to 1. Well, that's not true. I mean, that's not going to, that didn't work out either. That didn't work either, did it? Some. Yeah. I mean, I'm open to trying anything. You want to put x equals to tangent? You said? I mean, I'll try anything. You want tangent? Why not? Tangent t. What happens? So we get tangent squared t, right? Plus y squared times, well, tangent t, y equals to 1. That's actually kind of nice. That gives me tangent t y cubed plus tangent goodness gracious, tangent squared t. I can't do math. Goodness gracious. Tangent, I can't multiply here. Tangent t times y squared, right? So this times that gives me tangent cubed, rather. You know, I've lost the ability to multiply expressions. Let me just try again here. Tangent cubed t y plus tangent t y cubed, right? Equals to 1. So if I divide I actually think that this is somewhat hopeful because I just need to solve this for y. Right? Have I made my point that it's not always easy to parameterize an equation? That was my point. Okay. So I think, I mean, this is a relatively easy equation, and as you can see, I mean, I think it's possible, but it would require some ingenuity to actually do it, right? Ingenuity, which is apparently not present in the room at the moment, myself included. So that's fine. I suspect if I divide by y to the 4th here, maybe that's going to get me something. Because no, I mean, here, let me change the problem ever so slightly. It'll make it easy. If I just change this to a y, then it becomes easy. See, because then I have x cubed y plus xy squared equals to 1, which gives me, what's that?
You can change that to make y squared equal to negative tangent t.
You're saying the thing I just erased has a solution of y equals negative tangent t. Well, that's nice, but it's gone now. So you say y equals to minus tangent t.
Y squared is equal to minus
Y squared is minus tangent t. Oh, see, that's...
y squared is equal to minus tangent squared t.
That's still bad. See, because I can't put a square equal to a negative. Yeah. It's in the...
Outside of the
So this one here, guys. So this is xy squared. I want to illustrate. Let me just illustrate something here, and then we'll move on. Xy squared plus x cubed y minus 1 equals to 0. If I can write the equation like that, I actually know I can parameterize it because I know algebra. And so my suggestion here would be to set x equals to t. Because then I just have, or maybe I should even divide by, let me divide by x before I do this. This is y squared plus x squared y minus 1 over x equal to 0. All right. Now I'm going to set x equal to t. That gives me y squared plus t squared y minus 1 over t equals to 0. So what's y? Minus t squared plus or minus the square root of t to the fourth minus 4 times 1 times minus 1 over t divided by 2. In other words, y is equal to minus t squared plus or minus the square root of t to the fourth plus 4 divided by t divided by 2. And then you can choose a plus or a minus depending on where you want to parameterize this curve. In other words, this is a graph. I mean, this actually is the graph of two functions. It's minus x squared plus or minus the fourth x squared of the x to the fourth plus 4 over x divided by 2. If you can solve for y, then things get nicer, right? Admittedly. We will see that we can parameterize more things when we study polar coordinates a little bit later in the chapter, okay? Right, anyway, enough. So that's, yes, Joshua.
Would tan squared equal to minus y3 minus y cubed inside of
Y squared equals to what?
tan squared is equal. Oh wait, never mind. I mixed up.
Again, the general problem of finding a parameterization for a given equation is generally a very difficult and open-ended problem. There are theorems of advanced calculus that tell you when you can solve for y locally as a function of x, but they don't actually give you a technique to find a formula for it either. So it's kind of like last semester we learned that we can integrate any continuous function. That's a fundamental theorem of calculus. Says that an area function exists for any continuous function, right? So great, sine of x squared is continuous, so integrate it. You can't do that. Sine of x squared doesn't have an antiderivative that's accessible with elementary means, right? You're like, but I can do power series. Well, that's true, but we don't teach that in Calculus 1, right? And there is something like power series for solving these things, some sort of iterative procedure, but now I'm getting far into the weeds. So let's talk about calculus. Calculus of paths. All right, so we're given a trajectory, if you like. That means x is some function of time, right? And y is some function of time. So I think it's probably worth our effort to just spend 3 seconds to talk about vectors here. As a vector, r of t would be x of t comma y of t. So it's a pair of functions of time, one for x, one for y. So the position. If you differentiate, you can calculate dr dt, all right? And that is literally just dx dt, comma dy dt. That's how we differentiate a vector, component-wise. This is the velocity. Position. Velocity. Yep. Next is acceleration. D squared r dt squared, which is d squared x dt squared comma d squared y dt squared. This is, in fact, yes, the acceleration. All of these are vectors. I guess I should probably put little vector symbols to make myself feel like I'm doing better today. All right, there you go, vectors. Emphasize that they're vectors, which means they point in a certain direction. Of course, we usually call the velocity v, which is dr dt. And the acceleration is a, which, by the way, is dv dt. There you go. I just taught you all of Physics 231. Are you happy? No. It's about 25% of Physics 231 right there. But yeah. Okay, there's a little bit more to it. You know, how do you get from the position to the acceleration and back again? That's a lot of it. That's kinematics. Anyway, so there's how you differentiate position and acceleration, just component-wise. Yes, sir?
What does the symbol of VR mean?
Vector.
That was vector.
Yeah, this means vector. Here I can illustrate. So if this is a trajectory like this, if I pick an origin, now suppose this is the origin, right? Then R points out like this. I usually envision the position vector going from the origin out to the point where the particle is, right? Then, depending on the direction, the orientation of the path, let's suppose it's this way. The velocity will prove next semester when we study these things more carefully, and we have the appropriate technology. Of course, all of you will be there to enjoy this beautiful mathematics because you love math more than... Anyway, so let's see here. So the velocity vector points tangent like so. I don't know why you're laughing. I don't know what I'm talking about here. This would be v of t, all right? That's supposed to be tangent to the curve like that. And then the acceleration vector, where that points, is harder to describe, but I think for this one, it's something like roughly speaking. I mean, that's here. I'll draw one. I can. If you got circular motion, then the velocity. If you got constant speed circular motion, the velocity looks like this. All right. And if it's around, say this is the origin. Well, let's not say it's the origin. Let's say that the origin's over here. Then the position would be like this. And the acceleration points towards the center of the circle. Like that. And as you go around the circle, acceleration always points towards the center, and the velocity always points tangent to the circle like that. Assuming that it's constant speed circular motion. If the speed's not constant, then you can have a tangential component to the acceleration, which speaks to the thing speeding up. Anyway, this is, you get into these details in 231, right? Some of you are in there. I'm telling you things you already know. Great. All right. Well, anyway, this is a public service announcement mostly. What we'll be focusing in on here is a curve, all right, and it's going to be described by, x equals to x of t, and y is equal to y of t. Those are given functions of time, right? And let me just draw a curve like this. There you go. I'm going to pick out some different points on this curve and just try to describe to you geometrically what's going on. Like, I'll start out like right here. Let's suppose that the curve is oriented like this. So at this point right here, the tangent line would look like that, right? So you could describe its direction by a vector if you wanted, right? And let's suppose that this point right here is at time t1. So what would the direction vector be? It would be dx dt at time 1 and dy dt at time 1. This would be the direction of the tangent line. Does that make sense? So of course, if you want to embrace the physics notation, this is just the velocity at time 1. That gives you the so-called direction vector to the tangent line. I think at this point, I've kind of put the cart before the horse a little bit. I need to give you a definition. Definition L is line with direction vector A comma B if and base point. If R of t equals to P plus T times A comma B parameterizes the line. That's a vector definition. Here, I'll give you the scalar definition. In other words, if we have P is equal to, say, P naught P1, then we have X is equal to P naught plus TA, and Y is equal to P1 plus TB. This would be a scalar parameterization of the line which goes in the direction A comma B, right? How is direction vector related to slope? What's the slope of the line L? How does it relate to the direction vector? Excuse me.
So that was the derivative direction, or ET, right?
Slope is a number, right? I mean, so like, what's the slope? What's this? I mean, I can draw it on here. If this is my AB vector, right? What that means is we go over A units and we go up B units, right? So you go back, rise over run, right? So M, the slope, if you like, it's going to be B over A for A not equal to 0, right? But this is why the concept of direction vector is to be preferred over slope. The direction vector describes lines that point in any possible direction in the plane. Up, down, left, right, doesn't matter. Slope has two very important kinds of lines left out, right? Ones that go up and ones that go down. Those have infinite slope, right? But those have direction vectors like 0, something. Either positive or negative for up or down. Any question? No. So the slope would be b over a. So let's see here. If you're looking for this point up here is a very special kind of point, right? Let's suppose that happens at time 2. What can you say about time 2 and the derivatives here? Well, I mean, slope is 0. Slope is 0, right? Very good. What's the direction vector? It's always v. v of t2, which would be dx dt at time 2, right? dy dt at time 2. But what is that more specifically on the basis of the geometry of this curve? What is that? One of those is 0. Which one is 0? The y one, right? So this would just be dx dt at time t2, comma 0. And like you said, the slope is 0. Now, you can also talk about vertical tangents, like this guy over here, t3, let's say. That would be a place where we had a vertical tangent on my picture. So there, the direction vector, what would it look like? And there's the tangent line. And here, we would have the velocity at time 3. It has 0 in the x direction, right? And it's got dy dt at time 3. That's what it looks like. So what I'm trying to tell you guys is if you're studying a parameterized curve, you can figure out where you have vertical or horizontal tangents by looking for places where either one or the other of the derivatives is 0, right? Now, if both of the derivatives are 0, that's subtle. And we'll have to attack those with a little bit more thinking. It could be like a cusp in the curve or something, like a kink, corner. Those are subtle. But generically speaking, what's the equation for the tangent line to a parameterized curve? So equation for the tangent line to, let's say, x naught comma y naught at t equals to t naught, all right, is we can put x equals to x naught plus x prime of t naught times t, and y is equal to y naught plus, and let me give you a little bit better, y prime of t naught, and not times t, but let's make this times t minus t naught, and t minus t naught. These right here, this is the parametric equations for the tangent line. I would call this is the colliding tangent line. Why would I say colliding? You could also write it like this: L of t is equal to x naught comma y naught plus parentheses t minus t naught times the velocity at time naught. That's the vector version of those two. I've left my phone somewhere else. Forgive me for a second here. Let's actually work some examples, yeah? Well, let me get one more sort of general bit of information out here. Imagine that you did have a function whose graph lined up with your parameterized curve, right? Suppose you had a function, and maybe y equals f of x looks like this, right? Suppose that's y equals f of x. And suppose that this point right here corresponds to, say, let's say x of t4 is equal to x4, if you don't mind, all right? What would dy dx at x4 be equal to? Well, you know from calculus 1 that that should be equal to f prime, right? I mean, this is just notation at this point. F prime of x4, right? And what does this mean? This is the slope of the graph, right? How would that be related? Slope of graph at x equals to x4. How would that be related to the parameterization? How would that be related to derivatives of the functions? I mean, well, I just told you over here the relation between the slope and the direction vector, right? The relation is it's b over a. What's the direction vector at x4? Right? The direction vector is v of x4, which v of t4 rather, which would be what? It's x prime of t4, y prime of t4. So this should be equal to the rise over the run of the direction vector, right? It should be equal to y prime of t4 divided by x prime of t4. And so this is sort of a general idea, calculation, whatever you want, is to calculate dy dx at x of t. What you do is you calculate dy dt at that time t, and you divide by dx dt at that time t. And that will make sense, provided, of course, that dx dt is not what? If dx dt is 0, you've got no business making this calculation. But otherwise, this is how to get the slope of the corresponding graph. Yeah.
That's only if the curve is...
Not at a vertical tangent. Yeah. All right, let's work an actual example. So let's see. Suppose you got x equals to t squared plus 1, and y is equal to t cubed plus t squared. All right. Let's find the colliding tangent line to, let's say, t equals to 1. Also, find Cartesian equation of tangent line at that point. So what do? I calculate dx dt. What's that give me? 2t. What's dy dt? Yeah, 3t squared plus 2t. Very good. And t equals 1, right? So x prime of time 1 is just 2. Y prime of time 1 is 3 plus 2, which is 5. So I put those together. And by the way, also notice what is x of 1? X of 1 is what? It's 1 plus 1, which is 2, right? And what's y of time 1? Oh, it's also 2. Yeah. Hence, we have x is equal to 2 plus 2 times t minus 1. And y is equal to 2 plus 5 times t minus 1. These right here, folks, are the equations, the parametric equations for the colliding tangent line to t equals 1. The reason I say it's colliding is that both of these curves hit the point 2, 2 at time 1. So if you thought about the parameterization of the tangent line as being the trajectory of one car, and you thought about the given equations as the trajectory of another car, well, they crash at time 1 at the point 2, 2. That's why I call it the colliding tangent line. You'd still get the parameterization of a tangent line if you didn't put t minus 1 here. If instead you put just t, it would still give you a tangent line, the parameterization of a tangent line, but then it wouldn't be colliding. The tangent line would meet the point of tangency at a different time than the parameterization itself. And depending on what you're after, that might be fine. But I said colliding, so we're stuck with it. The Cartesian equation, how do we find that? Well, the hardest and most labor-intensive way to do it would be to solve both of these equations for t and set them equal. Right? If you're looking for the Cartesian equation, you can just eliminate time, right? That's one way you could do it. But I think a smarter way to do it is to use our larger discussion over there, right? The Cartesian equation should be y is equal to, let's see, well, my initial point is 2. That's y naught. And then what's my slope? My slope, rise over run, 5/2. And then I've got x, what's my minus 2? So there you go. That's the Cartesian equation for the tangent line. Generically speaking, let me remind you guys, if we want an equation for a line through, let's say, x naught, y naught with slope m, what do? We say y is equal to y naught plus m times x minus x naught, and that is the equation, the Cartesian equation of such a line. So I know the point 2, 2 is there. That's why I put a 2 here and a minus 2 there. And I know the slope is the rise over the run of the direction vector, so that gives me the 5/2. What's that? Uh-huh. Or in the French, ha ha ha. Sorry, I'm an idiot. That was already established. All right, let's see here. Example 2. We could look at x equals to t cosine t, and y is equal to t sine t. Actually, I had you guys look at this yesterday. Remember? At the end of class. This is more or less what you're looking at, the spiral. And we could do things like find the slope of this curve at time t. That's a much more friendly question, because then we just say, okay, so dy dx, right, at x of t, which is what's meant, this is the slope at time t for the curve. That would be dy dx at x of t. And the theorem of calculus tells us to do that. We just do dy dt divided by dx dt. It's just like we're dividing by dt above and below, isn't it? It's kind of funny. But that's actually it's honestly a theorem, which I have not really proved for you guys, but I argued by a picture over there. Anyway, dy dt was what? We got what? Sine t? Right. Plus what? T cosine t, right? Dx dt, cosine t, yeah, minus t sine t. So, yep. Now you could ask questions like, where are their vertical tangents, right? Where are their horizontal tangents? To find horizontal tangents, what do we want? Or I can't spell horizontal for some reason. Horizontal, yeah, that seems right. What do we need? Right. Which is the numerator, right? And to find vertical tangents, need solutions of dx dt equal to cosine t minus t sine t equal to 0. Now I can't find those using closed form methods. Those are numerical problems to solve those equations. But there's a nice graphical way to approach it. This equation actually is what? This is actually t equals to minus sine t over cosine t, right? Or if you like, you could trade that for tangent t equals to minus t. So to solve this equation, I just have to look at the graph of tangent. Right? And then I have to look at the graph of minus t, which is easier. And then every place I get an intersection, there's one I can find by hand, 0. And then this one. And then this one. These other ones will require a numerical method to actually find, but you could look at the graphs and find them, and those would correspond to the horizontal tangents. And likewise, this one, what do you got to do? You look at this being 0, that gives you t is equal to tangent t, right? So on the other hand, if you look at the same graph, but if you look at the line not very well to scale, t, right? Then these intersection points will be the, oh, look at that. 0 is both a vertical and a horizontal. See, I should be careful. I can't really say that dy dt equal to 0 necessarily gives me a horizontal tangent. If dx dt is also 0 there, I lose the right to say it's horizontal.